Dear friends, I am Dr. K. Kandan, Professor Mechanical Engineering, Anjalayammal Mahalingam Engineering College, Koilvanni. I am happy to meet you again on the video lecture in the subject Engineering Thermodynamics. This is module number 4. The topic is Availability and Irreversibility. Lecture number 1, first lecture on the Availability and Irreversibility. So we recap from the previous module or previous lectures. So earlier we studied about the first law of thermodynamics, application of first law of thermodynamics to the open system and the closed system. We studied the different forms of discussed different properties of the system like internal energy, enthalpy, entropy, the pressure, temperature, volume, and we discussed about the cyclic process. And in the second law of thermodynamics, we studied about the various heat pump, heat engine, and refrigerator. The COP of the refrigerator, heat pump, the efficiency of the heat engine cycle were discussed, and we defined entropy, and we calculated the entropy for different processes, different thermodynamic processes. So here the topic, the portion syllabus for the this lecture. So the high grade, low grade energy, available and non-available energy of sources and finite body, exergy and irreversibility, expressions for exergy of closed system, open system, energy balance and entropy generation, irreversibility, first and second law efficiency. So this is all the topic we are going to briefly discuss on this lecture. So the learning outcome. At the end of the lecture, the student will be able to distinguish between high grade and low grade energy, discuss the available energy and unavailable energy, and the student will be able to define useful work, availability and irreversibility, and the student will be able to define the second law efficiency of the system. So the high grade and low grade energy. The source of energy can be divided into two groups, namely high grade energy and low grade energy. We are using energy in different forms. For example, thermal energy, electric energy, chemical energy, magnetic energy, potential energy, kinetic energy, water energy, nuclear energy. So there are different forms of energy we are using. We are familiar with. The total number of forms of energy available, they are grouped into two. One is high grade energy, another one is low grade energy. The examples for high grade energy are mechanical work, electrical energy, water power, wind power, kinetic energy of the jet, and tidal power. The low grade energy, examples of the low grade energy, heat or thermal energy, heat derived from nuclear fission or fusion, heat derived from the combustion of fossil fuel. So all the forms of heat energy, it is called as low grade energy, and all the form of work energy or power, that is called as high grade energy. And there are some differences between high grade energy and the low grade energy. The complete conversion of low grade energy into high grade energy is impossible by virtue of second law of thermodynamics. So we studied about the heat engine cycle, so where the heat is given as an input to the engine, and the engine is producing work. So normally the efficiency of the heat engine is around 40%. That means only 40% of the total work input is converted into useful work. Total heat input is converted into useful work. The remaining 60% is sent to the atmosphere as a waste. So the complete conversion of low grade energy into high grade energy is impossible by virtue of second law of thermodynamics, whereas the complete conversion of high grade energy into low grade energy is possible. For example, you take a water heater of 1000 watts. So you put the water heater into your water, in a bucket of water, and switch on. So when the amount of heat generated will be equal to the amount of current given to the heater. So the electrical energy is a kind of high grade energy. So it is converted into low grade energy, that is heat energy. So the complete conversion of high grade energy into low grade energy is possible. In the conversion of low grade energy into high grade energy, the part of energy available for conversion is referred as available energy. And the remaining portion, the part of energy which is rejected, is known as unavailable energy. So available energy, the portion of energy which is converted into useful form. Unavailable energy, the part of the energy which is rejected to the surrounding. That is what the unavailable energy. So look at the cycle. So there is a engine working between the temperature T1 and the T2. So the source temperature is T1. So from the reservoir, the amount of heat given to the engine is Q1 quantity, and the engine is producing work, that is W, maximum work it is possible, whatever the possible maximum work is producing, that is called as available energy, and the amount of energy rejected at is Q2, that is what unavailable energy, to the sink temperature T2. So this is the source temperature T1, sink temperature T1, T2, the engine is working and it is producing work. So here we have two terms. One is available energy. The work produced by the engine is called as available energy, and the heat rejected to the surrounding is called as unavailable energy. So the maximum work obtainable from certain heat input in a heat engine cycle is called as available energy. So the maximum work is available energy, and the minimum energy rejected to the sink is called as unavailable energy, or UE. Therefore, Q1 equal to AE plus UE. So W max equal to AE, that is equal to Q1 minus unavailable energy. And for a given temperature T1 and T2, so eta equal to 1 minus T2 by T1. So T1 is the temperature of the source and T2 is the temperature of the sink. So now look at this equation. So for efficiency of the reversible cycle, so we are interested to improve the efficiency. We want to achieve the maximum efficiency. We say we want to achieve the maximum efficiency. So there are two possibilities here, 1 minus T2 by T1. So when you reduce the T2 value, so this ratio will decrease. When this ratio is decreasing, the efficiency will be maximum. So T2, so it is to be reduced. So this temperature of the sink, it should be as low as possible to get the maximum, to extract maximum work from the engine, or to produce more efficiency, maximum efficiency. Then for a given value of T1, the efficiency of the reverse cycle will increase with a decrease in T2 value. So we assume T1 is constant, right? So for a given value of T1, so the efficiency will increase by decreasing T2. The lowest practicable temperature of heat rejection is the surrounding temperature TO. So the lowest possible temperature is TO. That is what the lowest possible temperature. When it is rejecting heat to the surrounding, then the efficiency will be maximum. Now look at the diagram. So this is the heat supply process. So Qxy is the amount of heat generated, the heat supplied to the system, and this is the surrounding temperature TO, and this is the unavailable, and the shaded area is the unavailable energy, and the top portion in the TS diagram. So this is what the available energy, which is converted into useful work. So eta maximum equal to 1 minus TO by T1. So TO is the surrounding temperature, T1 is the temperature at which heat is supplied to the system to the engine. So W max equal to 1 minus TO by T1 into Q1, which is equal to Q1. So multiply Q1 minus TO into Q1 by T1. So Q1, actually here it is Qxy. So available energy equal to W max equal to available energy equal to Qxy minus TO into Q1 by T1 is the change in the entropy. So Sy minus Sx. So heat transfer by temperature is the change in the entropy. So the available energy equal to Qxy minus TO into Sy minus Sx. Unavailable energy is Qxy minus W maximum, which is equal to TO into Sy minus Sx. So the area of the rectangle is the unavailable energy, which is TO, the height is TO into Sy minus Sx. So unavailable energy is the product of lowest temperature of heat rejection and the change in entropy of the system during the process of supplying heat energy. So this unavailable energy, it is the product of surrounding temperature with the change in entropy for the given heat supply process. And this is exergy. So the available energy is also known as exergy, and the unavailable energy is also known as energy. So this is what the two terminology. So available energy, availability, all these things, it is referred to as exergy. So it is what the new terminology, new term for available energy. So the maximum work produced in a steady flow process. So we studied two types of processes in in our engineering thermodynamics. One is flow process, another one is non-flow process. That is, the process occurs in the open system. Say for example, gas turbine, steam turbine, internal combustion engine. So in the open system, the mass and energy crosses the boundary of the system. There is another class of another type of the process that is closed system, non-flow process or closed system, where mass remains constant, only the energy crosses the boundary of the system. Now we take the steady flow process, the maximum work in a steady flow process. We are writing the steady flow energy equation, W max equal to H1 minus TO into S1 plus MV1 square by 2 plus MG into Z1 minus H2 into TO S2 plus MV2 square by 2 plus mg into Z2. So here already we know the steady flow energy equation, H plus mv square by 2 plus mg Z1 minus H2 plus mv2 square by 2 plus mg Z2. So the minus TOS2 minus TOS1, this is added, mentioning that the system is interacting with the surrounding at temperature TO. The expression H minus TO into S is called as Keenan function B. So W max in terms of B, so B1 plus MV1 square by 2 plus mg Z1 minus B2 plus MV2 square by 2 plus mg Z2. So this W max equal to psi 1 minus psi 2, where psi 1 equal to the three terms B plus mv square by 2 plus mg Z. And psi is called as availability function for steady flow process. So the W max for the steady flow process. Now, when the kinetic energy and the potential energy is neglected, so W max equal to B1 minus B2, which is equal to H1 minus TOS1 minus H2 minus TOS2, or H1 minus H2 minus TO into S1 minus S2. For unit mass, divided by the mass throughout the equation, W max equal to B1 minus B2 into small h1 minus specific enthalpy. H1 is small hp is the specific enthalpy, small h1 is the specific entropy, and small b1 is the specific Keenan function, that is Keenan function per unit mass. So the b1 minus b2 equal to h1 minus TOS1 minus h2 minus TOS2, or h1 minus h2 minus TO into s1 minus s2. That is what the maximum work possible in a steady flow process. Similarly, maximum work in a closed system, that is non-flow process. So now W maximum equal to E1 minus TOS1 minus E2 minus TOS2 equal to E1 minus E2 minus TO into S1 minus S2, where this E equal to U plus mv square by 2 plus mg into Z. So U is the internal energy, V is the kinetic velocity of the fluid, and Z is the datum height from the datum. And W max here equal to U1 minus TOS1 minus U2 minus TOS2, or U1 minus U2 minus TO into S1 minus S2. That is the maximum work for a closed system. And again for unit mass, W max equal divided by the mass throughout, U1 minus TO into small s1 minus U2 minus TO into S2. So U1 is the specific internal energy and small s1 is the specific entropy. Similarly, U2 is the specific internal energy at the outlet, S2 is the specific entropy at the outlet. So W maximum equal to U1 minus U2 minus TO into S1 minus S2. And there is another work, useful work. So maximum work, useful work, what is the work available? Now you look at a system, the system is doing some work, the maximum work it is doing. But out of the maximum work, certain portion of work is given to the boundary to move the surrounding. Some energy is given to the surrounding to move, that is subtracted. The useful work is defined as the actual work delivered by the system less the work performed on the atmosphere. So what is the work performed on the atmosphere? We have to subtract it. So useful work equal to actual work minus PO into V2 minus V1. So PO is the surrounding pressure, V2 minus V1 is the look at the volume V2 is the final volume, V1 is the initial volume. So this is the useful work. So for closed system, WU maximum equal to U1 plus PO V1 minus TO S1 minus U2 plus PO V2 minus TO S2. That is what the for the useful work for the closed system. Then dead state, the atmospheric state. To be simple, the atmospheric state is known as dead state. So when the system is interacting with the surrounding condition is called as dead condition. So when the system is in equilibrium with the surrounding, it must be in a pressure and temperature equilibrium with the surrounding. So when the system interacting and coming to equilibrium with the surrounding, then the pressure and the temperature equilibrium with the surrounding, it must be also the chemical equilibrium with the surrounding. So in every respect there is equilibrium. There is pressure equilibrium, temperature equilibrium, chemical equilibrium, and there is zero velocity and minimum potential energy. So this state is known as dead state. The atmospheric state is called, atmospheric condition is called as dead condition, dead state. So this is the O is the normally we mention PO, TO is the pressure and temperature of the dead state or the surrounding pressure and temperature in all our calculation. So subscript O is referred for the dead state or the surrounding temperature and surrounding pressure. Availability. So the important parameter is availability. The availability A of a system is defined as the maximum useful work that is obtainable in a process in which the system comes to equilibrium with the surrounding. So surrounding, I mentioned earlier, the surrounding is called as dead state. So the availability of a system is defined as the maximum useful work is obtainable in a process in which the system comes to equilibrium with the surrounding is called as dead state. So availability of steady flow process, the maximum work associated with the steady flow process. So already we defined W maximum equal to H1 minus TO S1 plus half MV1 square by 2 plus MGZ1 minus H2 minus TO S2 plus MV2 square by 2 plus MGZ2. So that is what the maximum work obtainable in a steady flow process. When the system comes into equilibrium with the surrounding, so this becomes, so the H2 becomes HO, S2 becomes SO, VO velocity is 0, so that this time is dropped, and Z2 becomes ZO, and this is simplified H1 minus TOS plus MV square by 2 plus MGZ minus HO minus TOSO minus MGZ2, and for the availability per unit mass, so dividing by the mass throughout. So here for the mkg of the system, mkg of the fluid, now we reduce the equation per unit mass. So small a equal to small h minus TO into S plus V square by 2 plus GZ minus HO minus TOSO plus GZ2. The decrease in availability or maximum work obtainable per unit mass. So this is W max equal to A1 minus A2. So you substitute everything. So this is a general function of availability function. So here we substitute for A1, so H1 plus TOS1 plus V1 square by 2 plus GZ1 minus HO minus TOSO plus GZ2, and for A2, H2 minus TOS2 plus V2 square by 2 plus GZ2 minus HO plus minus TOSO plus GZ2. So when you mathematically, so the second term and the fourth term are getting cancelled. So finally what is left out? H1 minus H2 plus TO into S1 minus S2 plus V1 square minus V2 square by 2 plus G into Z1 minus Z2. So this is the W max availability, the change in the availability, decrease in the availability or increase in availability, the change in the availability, which is what the maximum work obtainable from the system in a steady flow process. Now when you neglect the kinetic energy and potential energy, the availability of steady flow process, H1 minus TO S1 minus H2 minus TO S2, or it is also known as B1 minus B2. This is what we earlier discussed. And the availability of non-flow process. So the maximum work, again the definition is the maximum work obtainable or availability of a non-flow process when the system comes into equilibrium with the surrounding, that is the dead state. So already we defined W max equal to A equal to E minus EO plus PO into V minus VO minus TO into S minus SO. So substituting for the terms, E equal to U plus MV square by 2 plus MGZ minus EO equal to UO plus MGZO. So velocity becomes 0. That is why velocity is dropped here. Plus PO into V minus VO minus TO into S minus SO. So this is the availability function for non-flow process. Now neglecting the kinetic energy and the potential energy, the availability per unit mass becomes U minus UO plus PO into V minus VO minus TO into S minus SO, or grouping the terms U plus POV minus TOS minus UO plus POVO plus minus TOSO, and this is called as phi minus phi O, where phi is called as availability function for closed system. So earlier for steady flow system, we found that psi is the availability function. Now here we are using phi is the availability function for the closed system. And if the system undergoes change of state from 1 to 2, then the decrease in availability of non-flow process, W maximum, is the change in the availability is the maximum work produced by the system, non-flow system, which is pi 1 minus pi O minus pi 2 minus pi O equal to pi 1 minus pi 2, which is U1 minus U2 plus PO into V1 minus V2 minus TO into S1 minus S2. So this is the maximum work produced by the non-flow process or closed system. And the property Gibbs function is defined as G equal to H minus Ts. So G is the Gibbs function, H is the enthalpy, T is the temperature, and S is the entropy. And the Helmholtz function is defined as F equal to, F is the Helmholtz function, U minus Ts. So U is the internal energy and T is the temperature, S is the entropy of the system. And we define the irreversibility. The difference between the maximum work and the actual work is called as irreversibility of the process. So actual work, which is what available, and the maximum work, which is possible. So the possible work is maximum work when the system is getting in equilibrium with the surrounding, and the actual work is what is the real work produced by the system, that engine or the device. It is also referred as degradation and dissipation of energy. So irreversibility is called as degradation of energy, so the second law itself, that is called as law of degradation of energy. So I equal to W max minus W, which is equal to TO into delta S system plus delta S surrounding. So we substitute for W max and W and simplify, we will get delta S TO into delta S system plus delta S surrounding, which is equal to TO, the surrounding temperature, into delta S of universe. And Gauss-Stodola theorem, the rate of loss of available energy in a process is proportional to the rate of entropy generation. Earlier we discussed the irreversibility, which is known as the maximum. Actually, the difference between maximum work and the actual work, the rate of loss of available energy in a process is proportional to the rate of entropy generation. That is, I equal to work lost. Work loss equal to TO into delta S universe. That is what we derived earlier, which is equal to TO into entropy generation. So that is what the Gauss-Stodola theorem. And the first and second law efficiency. First law efficiency already we defined. So in the heat engine we defined efficiency equal to work output divided by the heat supplied. So the work output energy of a device divided by the input energy of the device. The second law efficiency is minimum available energy divided by the actual available energy. So A minimum by A, or otherwise we will calculate the second law efficiency is a ratio of first law efficiency divided by the Carnot efficiency or theoretical efficiency. So first law efficiency is very simple. Work output divided by the heat supply. Second law efficiency equal to the first law efficiency divided by the Carnot efficiency. So we stop here. So these are all the reference book I used for preparing the slides. You can also refer to it for additional information, and you can write to my mail ID for any clarification or doubts. So I will sincerely answer. Please subscribe the channel. So I have uploaded all video lectures on the thermodynamics, heat transfer, all the thermal engineering subjects, and also I have uploaded the YouTube video on gate solution on mechanical engineering subjects, so which will be useful for your learning. So thank you very much, and we'll meet again.